Okay guys, so this video will be about heating curves and phase diagrams. And what heating curves do is they help us to calculate the change of enthalpy that occurs when a change of state happens. So say that you have, say, ice or some solid, it could be any solid, we'll use ice. So you say if you had ice and you added heat to it and you formed water at a certain temperature, or maybe you took water and you formed steam, or maybe you went all the way from ice to steam. What heating curves allow you to do is it allows you to calculate how much heat, how much energy will be required for that change. And then we'll also talk about phase diagrams. Now what phase diagrams do is they don't allow you to calculate energy, but what they do is it's a nice graphical way of representing what pressure and temperature combinations would lead to certain states of matter. So with that in mind, let's go ahead and get going. Calculating energy for a change of state. So this is the first thing we have to do. Before we get to heating curves, we have to talk about, in general, how do we calculate how much heat is required to make, say, a solid go to a liquid, or a liquid go to a gas. So when we have a solid go to a liquid, that will be, depending on which way you're going to go, this will be like the heating / melting process. And we've talked about how in freezing, it's an exothermic process, and so energy will be released. Essentially, bonds form between the molecules, and these intermolecular forces form, and so that's going to lower the energy of the system, and the rest of it gets put out as heat. Melting requires you to put energy into this, and we can talk about what's called a heat of fusion for this. So a heat of fusion, and very often this is abbreviated delta H fusion. The units of this, it could be various units, but in general, it could be kilojoules per mole. I've seen that. It could be joules per gram. Okay, it could be joules per mole. But so anyway, from that unit, you can see that the heat required for freezing or melting would simply be whatever the heat of fusion is for that substance. And every substance has a different heat of fusion. Water would be different than lead, which is different than iron. So each one has a different heat of fusion. So it'd just be the heat of fusion times the mass or the number of moles, depending on, it really depends on what this unit is right here. Okay, so this would be mass or moles. Okay, one or the other. And so this equation allows us to calculate, if I had a certain mass, a certain number of moles, how much heat would be required to melt it, or how much heat would be released if it were to freeze. Now notice that there's no negative sign in here, so it's going to be up to you to keep track of which process is exothermic and which process is endothermic, so make sure you do that. Now, so this is going between solids and liquids, right? To go between liquid and liquid and gas, we would say that we have boiling. Oops. I'm not sure how that happened, guys. Let me get that back. So we would have boiling, or we would have condensing. Okay, so boiling or condensing, and this would be the heat of vaporization. Okay, so we abbreviate that delta H vap. It can have the same units, so we're talking about kilojoules per mole or joules per gram here. Okay, and for this one, to be Q is equal to delta H vap times, once again, the same M. Okay, so the point of this is that when we have this change of state, we have to use one of these two equations. Now, what's not in these equations is a delta T. So remember, when we were doing calorimetry before, and we were talking about, say you had a metal and it cooled from one temperature to another, or you had water that warmed from one temperature to another, we use Q equals MC delta T for that. And for a change of state, the temperature doesn't change. So the heat that we're adding or the heat that we get away is due to, it's going to go towards either breaking intermolecular forces or it gets dumped out after intermolecular forces are created. And there's no change in temperature that occurs. So there's no delta T in this. Okay, so with that in mind, we're going to go to heating curves. And for heating curves, this is just kind of a nice visual way to put this all together. So say that I wanted to heat ice up. So I wanted to go from ice at negative 20 degrees C to, let's just go all in, to steam at 110 degrees Celsius. We'll assume we're at 1 atmosphere. So what we'll do for this heating curve is we can have temperature on this axis, and in this case we will have heat added on the bottom axis. And we will start off at this temperature of negative 20 degrees C, and we will gradually increase in temperature up until we hit this melting point at 0 degrees Celsius, and it's going to flatten out, okay, until it's all the ice is converted into water, and then the water will warm up, and that will go until we hit 100 degrees Celsius. Okay, it's going to flatten out as we go from liquid to gas, and then it's going to increase until we hit our final temperature of 110 degrees. Wow, that's pretty high. 110 degrees Celsius. 110 degrees Celsius. All right. So this is kind of what the temperature would do as we add heat. And in each section, we can think about the state of matter that we have. So here we would have solid. Here we would have this transition between solid and liquid, so they both exist. Here we have liquid. Here we have a liquid plus gas, and here we have just gas. Okay, and we would need to calculate the heat added for each one. So for this first one, here we use Q, M, C, so in this case it's ice. And ice does have a different specific heat than water, so you gotta watch out for that. Times the change in temperature. And this is just what we did before. Okay, here it would be Q is equal to the heat of fusion times the mass or number of moles. Here is Q equals MC. This is for water. Liquid water, I should say. Delta T. Okay. Here, Q delta H VAP times M. And here will be Q M C. This will be for steam. Delta T. Okay, and all we would do is we would add each of these up. So we would calculate the heat for each one. We would add them all up together, and the addition of this is how much heat would be required to heat a certain mass of ice at negative 20 up to 110 degrees Celsius. Okay, so it's really easy. I mean, it's a little tedious, I guess, but it's a very easy kind of step-by-step process. It's, just each one separately, then you add them all together. Okay, and that's all a heating curve is. You can do this for any substance, as long as you know the heat of vaporizations, the heat of fusions, the specific heats you want. You could also have heat evolved or given off. That would kind of be going down the other way. You start at high temperature, go low temperature. You can do that as well. All right, so that's heating curves. Another way that we kind of express changes of state are with phase diagrams. And so these phase diagrams, we've seen these before. But what we would have is these are pressure, temperature diagrams. Okay, and when you look at these, you'd see some lines on them, right? So you would have like kind of a line going up. You'd have kind of a dot here. You'd have a line going up this way, and then usually like a little curvy line going up this way. Okay, and what these boundaries are on these lines is where we have a change of state occurring. So let's think about what we have in each section here. If we have a low temperature and high pressure, then we will have a solid. And so this whole region, if you have a pressure and temperature anywhere in this region, it'll be in the solid state. And if you have a high temperature, low pressure, you'll have a gas. And so this whole region is where the gas is. And then that means this middle region is where we have a liquid. And so what these lines are is if you happen to be at a pressure and temperature that falls on a line, it means that you have a change of state occurring between the two, right? So if you're right here, that would be a melting point as you're going from solid to liquid at whatever pressure you're at. And if you're along here, you'd be at the boiling point. Okay, which means right here, oh, and down here would be going from solid to gas. This is where sublimation is occurring. It's on this line. Which means right here, we would have a triple point. Okay, now this triple point is a very unique point. Each substance, each pure substance would have. And by the way, these phase diagrams, as I've shown it, are for pure substances. You can do phase diagrams for solutions, but you don't worry about that till later on in college. So anyway, this will be the triple point. At the triple point, solid, liquid, and gas exist in equilibrium indefinitely. So if you were at that very specific pressure and this temperature, you would have all three substances occurring or existing at the same time in equilibrium. Okay. So this is the normal one. I'm going to call this normal. I'm going to put parentheses around it. This is normal. Now, there is a phase diagram that you guys should know about that is not normal, and that's because it's the phase diagram for water. And let me show you why water is weird. Because water will have a phase diagram, will go up like this. You have a triple point. You'll have this, once again, but then the line between solid and liquid has a negative slope. Let's see why that is significant. All right, when water does this, I think there might be some other substances that do it as well. But when you have this negative slope line between a solid and a liquid, what that means is that the solid is actually less dense than the liquid. Because as you're increasing pressure, it's going to try to form the most dense state of matter possible. And so for most substances, that's going to be solid. As you increase the pressure, it's going to go from a liquid or a gas to a solid, and that makes sense, right? The solid's the most dense state of matter. But for water, because of the hydrogen bonding, because of the honeycomb network that it forms, as you increase the pressure, it actually forms a liquid state. There's less kind of space within liquid water than there is between solid and solid ice, and it's a good thing. That's why ice floats on water. It's why when the lakes, rivers, oceans freeze, ponds, the ice stays on top, which means all the life below can exist, and over time it can evolve and form things like us. So no, it's very fortunate for life on Earth. It means a lot of the liquid water is not locked up in ice, and so we don't have a desert planet. And so yeah, so anyway, this negative slope here, what that's telling you is that the liquid is more dense than the solid. And also for all of these, there's kind of a critical point. If you get above a certain temperature, no matter what pressure you have, if you get above a certain temperature, then you will not be able to to form a liquid. It's called a supercritical fluid. So you're kind of be in the gas phase. It has very unique properties. It is used industrially, but I just want to mention that there is a critical point. Okay, and so above this critical point, once you get above this critical point, you can no longer have a liquid. Okay, all right. So that's about all I have, guys. I hope you learned something, and if you have any questions, please let me know.